Hello and welcome to Dr. Clay's Chemistry Lessons. Today we're going to be looking at the AQA A-Level Chemistry and we're going to be looking at transition metal catalysts. Okay, don't forget to check the cards in the top right hand corner to get links to Dr. Clay's A-Level Chemistry, helping you to improve your grades using heaps of resources, plenty of webinars along with all of my YouTube video content. By the end of this session, we should be able to do the following. Describe why transition metals can act as a catalyst. Explain the difference between heterogeneous and homogeneous catalysis. Explain how Fe, that's iron in the Haber process, and vanadium in the contact process act as catalysts. Explain how the reaction between MnO2- and I- is catalyzed by Fe2+, and explain the autocatalysis of ethane diorate by MnO2-. So first of all, let's look at how transition metals act as a catalyst. Well, catalysts here all work in a very similar way. Here we've got an energy profile diagram. We've got enthalpy or energy up the left-hand side and progress of reaction along the bottom. On the left-hand side, we've got the reactants, and on the right-hand side, we've got the products. This happens to be an exothermic reaction. It doesn't really matter if it's endothermic, it just shifts the position of the products. What we observe here is the red line is the energy profile for an uncatalyzed reaction, and it's got an activation energy, which is a difference between the products here, or the starting reactants, and the intermediate state. A catalyst, however, remember, offers a different pathway with a lower activation. Now, transition metals do this in one of two ways. They either offer a surface for something to stick to and then an exchange of electrons to happen, and therefore there's normally an activation energy to get to that and then another reaction. Or when we're talking about things in the same phase, we might have a molecule which comes and sticks to the complex ion, which has an energy, and then another reaction as electrons gets changed and another reaction occurs. But either way, the total activation energy here of the two catalyzed reactions is lower than that of the overall uncatalyzed reaction. So the first thing we're going to look at in catalysis is in heterogeneous catalysis. And heterogeneous catalysis simply means different state. And what we're looking at here is we're going to be looking at reactions which are in the gas phase and our catalyst, which is going to be a solid catalyst. So these two things are in a different state. The way this thing works is that you end up with the solid catalyst sitting in a reaction vessel, and then you'll have gas molecules, perhaps joined together somehow, coming down and then sticking to that surface. It's called physisorption. And then there'll be electron transfer, and then the molecules of the atoms, once they've reacted, would then desorb from the surface. Now, as far as we're looking at in AQA here, once they've reacted here. As far as the AQA is concerned, we're really interested in knowing two specific heterogeneous catalytic reactions and the idea that we're looking at catalysis in different states. Our first example then comes from the contact process, which is the process in which we use to make sulfuric acid, and it's the reaction between sulfur dioxide and oxygen to make sulfur trioxide, which we catalyze using vanadium oxide. Now, if you work out the oxidation state, we've got 5 oxygens, so they're each -2, gives us -10. We've got 2 vanadiums, so we're actually catalyzing this with vanadium 5 oxide. It's catalyzed in a two-step reaction, with the first step oxidizing the SO2 to SO3 and reducing the vanadium from vanadium 5 here to vanadium 4. With the second step reoxidizing the vanadium 4 back to vanadium 5 by the addition of the half O2. And if we look at the overall reaction, well, if we cancel out our vanadiums here, we end up with an overall reaction of SO2 plus a half O2. The second industrially important heterogeneous catalysis that we're interested in is the Haber process, and here we observe the reaction of nitrogen and hydrogen both in the gas phase with a solid iron catalyst making ammonia. Now they don't ask us about the mechanism here because quite simply it's not very well understood. So all they're interested here is that iron can act as a heterogeneous catalysis in the Haber process. Now this particular reaction isn't highlighted in the specification at the A2 level, but it is one that we've met in the Year 1 syllabus, and that's a catalytic reformation of carbon dioxide and nitrogen from carbon monoxide and nitrogen monoxide in the car exhaust. Now, this highlights a point that they do want us to be aware of with heterogeneous catalysts, is that we often use a support medium. In other words, we have here a rhodium catalyst. Now rhodium is very expensive, and to make a large lump of rhodium would be quite an expensive and pointless activity. So what we do is we use a honeycomb support, and what this allows us to do is to use a very thin layer of rhodium, maybe just a couple of atoms thick, which means that we can reduce the costs. So the support medium allows us to reduce the cost, but also if we make it honeycomb we can increase the surface area, both of which are beneficial for the reaction but also for the cost of the production. Poisoning then is a reaction that we observe with heterogeneous catalysts, and it stops the catalytic behavior of the catalyst. In particular here are car exhaust. If we have lead come in, then it will sit or bind to the catalyst, and therefore it will reduce the chance of the reactants, the carbon monoxide and the nitrogen monoxide, getting to the rhodium catalyst. And what we say that this blocks the active site of the catalyst and therefore reduces the catalytic activity, and in this case the carbon monoxide and nitrogen monoxide wouldn't react. So here we go, poisoning. The final section then in catalysis is that of homogeneous catalysis, and homogeneous simply means same state, and in the transition metal chemistry we're really talking about aqueous state, and we've seen this a lot in organic chemistry so far with acids and bases catalyzing reactions, but now we're going to look at it specifically with transition metals and these catalysis. The one that we are interested in is the Proxy disulfate reaction with iodide ions and iodine, making the 2SO4 2- or the sulfate ion. And what we find is this reaction is very slow to start with, and we find that it's slow because the S2O8 2- and the I- are both negative. So we've got two negative ions, and the result of two negative ions is that they are going to repel one another and therefore less likely to react. This reaction then is catalyzed by that of Fe2+, and it's done so in a two-step reaction. The first step we see here is that proxy disulfate, that's the S2O8 2- and the Fe2+, attract, because we've now got a positive and a negative ion, and we form Fe3+ and the SO4 2-. The Fe2+ there getting oxidized and the S2O8 2- getting reduced. The second step then is Fe3+ plus 2I- making Fe2+, with the Fe3+ being reduced and the I- being oxidized back to iodine. Now, if we are to cancel out the Fe's from either side of this reaction, what we end up with is an overall reaction that we see above, and hence a catalyzed reaction. This reaction can be catalysed by Fe2+ or Fe3+, and that's because it doesn't matter which one we use, since they're equally likely to react. They're each formed in the reaction either as Fe2+ or as Fe3+, so either one can be used. The next reaction then that we're asked to look at is the autocatalysis of manganate MnO4- with ethane dioate, which is C2O42-, and they react to form Mn2+ and CO2. You see here on the right we've also got a graph showing how the rate of reaction occurs with time. Now it's slow to start with again because we've got two negative ions that repel each other, and therefore we see the rate of reaction here at the start of our reaction to be very slow. It's almost no change in reaction rate. But after a given time, the reaction rate starts to speed up. There we go, there's our first point where we see that it's slow while we've got two negative ions repelling. But the catalysts for this reaction are actually Mn2+ and Mn3+, and they work by attracting the negative ions. Here we have the reaction, so we form Mn2+ to start with, and they then attract the negative MnO4- ions that we observe and reform or form Mn3+ plus 4 waters. Here we start to speed up the reaction, and in the second step of this reaction, the Mn3+ reacts with the ethane dioate to form the Mn2+ and our carbon dioxide, which are products for our reaction. What this means is we then have a second phase of our rate of reaction diagram where we get an increased speed and the slope drops very rapidly. Then as we get to this last phase, the reactants start to become all used up, and there is then no longer any reactants with left to react, and so the rate slows right down. Okay, thanks a lot for watching. Please do check out my videos here at Dr. Clay's A-Level Chemistry. You've been watching Transition Metal Catalysts. You should be able to know the describe why transition metals can act as a catalyst, explain the difference between heterogeneous and homogeneous catalysis, explain how Fe in the Haber process and vanadium in the contact process act as catalysts, and explain how the reaction between MnO2- is catalyzed by Fe3+, and explain the autocatalysis of ethane dioate by MnO2-. I look forward to seeing you next time. Bye for now.